theorem. For all real numbers x, square root of x squared is equal to the absolute value of x. So let's prove this powerful theorem. There are three cases. X is greater than 0, x is equal to 0, or x is smaller than 0. In this case, we are using two uh, axioms, or we are using two properties of equality. We use a reflexive property of equality, respectively reflexive axiom, and we are going to use a substitution property of equality or substitution axiom. If x, the first case, if x is greater than 0, then square root of x squared is equal with x, and also absolute value of x is equal with x. Because x is equal with x, here we are applying the reflexive property, then x is equal with absolute value of x, and x is equal with square root of x squared, then here we can use the substitution property of equality, and then square root of x squared is equal with the absolute value of x. Second scenario, we have if x is equal to 0, then square root of x squared is equal to 0. And also the absolute value of x is equal with 0. So 0 is equal with 0 according to the reflexive property. Then 0 is equal with absolute value of x, and 0 is equal with the square root of x squared. Then we are using a substitution property of equality, so square root of x squared is equal with the absolute value of x. So the second scenario is proved. We are trying to prove the third scenario. When we have x is smaller than 0, then the square root of x squared is equal with minus x, and the absolute value of x is equal with minus x. Minus x is equal to minus x according to the reflexive property. But we know here minus x is equal to the absolute value of x, and minus x is equal to the square root of x squared. Then we are using substitution property of equality, so the square root of x squared is equal to the absolute value of x. So for all real numbers x, it means if we have, for example, x is a rational number, is irrational number, or natural number, whole number, then if a square root of x squared is equal to the absolute value of x, is going to hold for all these cases whenever x is a real number. But now, since the absolute value square root theorem is proven, let's go to take some example how we can apply the absolute value square root theorem in other situations. For example, here we have one example. How do you see it? Without finding points, match the function f of x is equal to the square root of 64x squared, and g of x is equal to the cubic root of 64x in exponent 6 with their graphs. Explain your reasoning. So here, what we have here, just let me take this one and erase. And what we have here, we have two graphs. So first of all, let's go with function f of x, and let's try to simplify it. And f of x is equal with let me simplify a little bit here. Let me write the square root here, and because the 64, I want the 64 to write as a square number in 8 square, because already 64 is a square number. I can write as a 8 square, and here x square. And let me simplify a little bit further this. Let me make in a better position so we can see much easier what is inside the radicand. F of x is equal with the square root, and here let me write a parenthesis 8x, and let's write as one monomial in a square here, and here is 2. So if I simplify further, so we already know the power 2, I can simplify with the index 2, and what remains in a f of x after I simplify, f of x is going to be equal with the 8x, and here we are applying the absolute value square root theorem. because here I have square root, and whatever here I have in the square, and if I'm simplifying this, I can write as an absolute value, is because I'm applying the absolute value square root theorem. So this is the same form like we have in this case, but instead in that example we have, instead just x squared, we have a 8x squared. Everything in a square is equal with the simplified form with the absolute value. So already I know from this situation which graph of the function belongs into the family of the absolute value. And absolute value always are very steep, very like linear functions, but they are in the form of the v, and here are a uh, very thick, very thin, or how to say, here is in form of the v, is not smooth here. So this function f of x, this graph of the function represents the family of absolute value of the function. I already can see it right now without doing anything in the g of x. But if we are trying to find the g of x, just let me simplify and let's see what g of x gives us. And g of x, if I'm simplifying, and here is a cubic, and instead of a 64, I see this is a cubic number. I can write like a 4 cubic. And if I'm looking x in a 6, I will write x in a 6, so I don't have to do anything there. And if I want this one to simplify, to get rid of the cubic root, I can get rid of the cubic root in a simplified form, and we can write 4 cubic under the cubic root is just a 4, and x in a 6 in a cubic root is just a x squared. We already see this is a quadratic function. Quadratic function, they have the graph in the form of the parabola. As we see, this graph in the figure B is in the form of the parabola, and this graph of the function is a function g of x. So let's see in other cases how we can apply again the absolute value square root theorem. It says write two variables expressions involving radicals, one that needs absolute value in simplifying and one that does not need absolute value. Justify your answers. And here, if I'm writing one expression, let me take one that I can write in absolute value. I'm taking the square root because here I can apply the absolute value square root theorem. And this one I'm taking one number that I can simplify. Let me take here is x squared, and let me make a little bit more interesting. Let me write here a y in exponent 4. And the other example that does not need to use the absolute value, let me take one cubic root because it's not a square and it's not related with absolute value. And here let me take 8, and let me take x in exponent 3, and let me take a y in exponent 9. Let me make a little bit different. And now I'm trying to simplify first of all that I have in a square root, but because here I'm going to use this absolute value square root theorem, this I can write in a form of, if I'm simplifying, square root of 4 is going to be 2, and x squared under square root is going to be just the x if I want to release from square root, and y in a fourth in under square root is going to be just y. So now y squared. So now I can write in the absolute value. So here we are applying the absolute value square root theorem. But because the y squared can be always a positive and 2 is a positive here, just a number, I can write this like a 2y squared, and x can be negative or a positive. We don't know exactly. That's why I want to make to be on the safe side. So I am writing in absolute value. Here in these cases we should apply the absolute value square root theorem. But in these cases, and as the question asking here, I can use the absolute values. In this case, I don't need to use the absolute value because 8 in a cubic is going to be 2, and it's not related with the absolute value square theorem. And this is x, and the y in a 9 is going to be y in exponent 3. And now let's go in another example. Says solve quadratic equation by using square roots. If we are using a square roots, let me use the square roots of both sides. And I have a x squared here and is under square root. Let me write a little bit with the long steps. N is equal plus minus, when we take a shortcuts, is square root of 9. So x is going to be equal with plus minus 3. So in this scenario, if I have a x and it was here, for example, in a square root of 9, this we can write, and this is equal with this, we can write in the absolute value of 3. So here we can apply the absolute square root theorem. That's why this have two signs. And then plus minus 3, this we can write x is a minus 3, or x, let me write here x is equal with a positive 3. So this is why we sometimes we take a shortcuts, but in reality is when we write everything in square root 9 here in this case, we can write this we can apply here the absolute value square theorem. We write in the absolute value, and when we have an absolute value, we have two values, can be x minus 3 or x is equal with 3.